Introduction to the normal distribution. Let's suppose we have Zippo thermometers. They're pretty cheap. We're measuring the temperature at which water freezes at standard pressure. So check this out. It's supposed to read 0 degrees Celsius, but these things are really in error. That's right, we got them for like 25 cents a piece, so we're happy. But so let's suppose we describe this distribution of Z thermometers, Zippo thermometers, by putting 0 here, 1, 2, 3, and we have this normal curve going over here. And by the way, what happens at this -1 is there's a point of inflection for you calculus nerds. But let's suppose we wanted to know how many of these thermometers would read less than 1 degree. So what's the total area or total percent out of 100% altogether that would be measuring below 1 degree? Well, it just so happens that we have a Z table for Zippo thermometers in our deal, and so if we look at 1Z at going over to 1 on the Z score there, it's 0.8413. So what that tells us is we have 84.13% of all thermometers are reading below 1 degree. And if we wanted to know how many are reading below 2 degrees, we get to go to this Zippo table and go down to 2 and know that it's 0.9772. So we've got like 97.72% of all thermometers are reading less than 2 degrees. That's pretty neat that we got a table like that for these Zippo thermometers. And what's probably the Zippo thermometer is going to read less than 2 degrees when we're measuring the point at which water is freezing? Well, we can go down here and we can go to the table right above it, which is negative Zippo values, and we can go to -2 and find the area below that is 0.0028. So we can go down here and say, well, altogether then we have 0.028% of the thermometers down there. Well, let's look at another normal distribution. So here, let's look at this one. What we have here is with these Zippo thermometers, this Z distribution, here's the mean at 0 degrees. It just so happens that it's symmetric. We get about 34% of thermometers reading between 0 and 1 degree when we're measuring the point at which water is freezing. 34% in here, 13.5, and so on. So like we saw from that table, we can know that the approximate probability that our Zippo Z-score is less than 1 degree is equal to the 50% below the median, because the mean and the median are the same, so there's 50% down here, and then another 34% there. So altogether, the area below that is 0.84, which means approximately 84% of all these Zippo thermometers is below 1 degree. Well, what if we were looking at height in inches of adult women? Women's heights are distributed normally with a mean of a certain amount and a standard deviation of a certain amount. Just so happens those amounts are a mean of 65 inches and a standard deviation of about 2.5 inches. So what happens is if we put the mean here and we go 1 standard deviation this way, look at these percentages. These are the ones we saw with the Zippo thermometers. Now I have a confession to make. The Z-score for the Zippo thermometers is not really a Z-score for Zippo thermometers. It's a Z-score which tells us in any normal distribution the number of standard deviations we are away from the mean. So it is a location or a position on the x-axis. So for that reason, if we go here at 1 standard deviation above the mean, this is a Z-score of 1. If we're 2 standard deviations below the mean, this is a Z-score of -2. A woman who's exactly as tall as the mean, which is 65 inches, would have a Z-score of 0 because she is 0 standard deviations away from the mean. So a Z-score tells us how many standard deviations away from the mean we are. And in a standard normal distribution of these Z-scores, the Z-scores are distributed normally with a mean of 0 and a standard deviation of 1. This Z-score is called a standardized score. And we can use the empirical rule that tells us that 68% of all scores are within 1 standard deviation of the mean. So, remember how we had 34% and 34%? They add up to give us 68%. So we have 68% of the scores within 1 standard deviation of the mean in either direction. with between a z-score of -1 and 1, because the z-score tells us where we are on the x-axis. So a woman who is 62.5 inches tall to one that's 67.5 inches tall. 1 standard deviation below and 1 standard deviation above. Now, if we're within 2 standard deviations, remember how it was 34% and then 13.5%? If we combine all those, then we get approximately 95% of all scores in a normal distribution will be within 2 standard deviations of the mean in each direction. So from a z-score of -2 to 2. And then if you go 3 standard deviations in each direction, you will trap about 99.7% of all scores, or in this case, of all heights of adult women, within 3 standard deviations of the mean. The mean's at 0 for a z-score. We're talking about z-scores from -3 to 3 because a z-score is a standardized score. It tells us how many standard deviations from the mean we are. 1, 2, 3. So we are at 3 standard deviations above the mean. A z-score of -3 means we are right there, 3 standard deviations below. This is a very important rule, the empirical rule, otherwise known as the rule of 68, 95, and 99.7%. Okay, so again, if we go back to the height of women, if we say, okay, suppose we randomly select a woman and we want to find the probability that this woman's height is less than 67.5 inches. That's what this nomenclature means, this little scripting right here. So all we have to do is use the empirical rule, and we can say, okay, look, this person is 1 standard deviation above the mean, so she is at a z-score of 1. Her height is right there. Using the rule of 68, 95, and 99.7, we remember that 68 is here, so half of that is 34. So that 34% plus the half of women whose heights are below the mean of 65 inches. So we got 50% here and 34% here. So this woman has 84% of other women have heights that are below her height of 67.5 inches. Now, what we can do is we can, instead of just using the empirical rule and approximating, we can convert a score from a non-standard normal distribution, like women's heights, whose distribution is normal with a mean other than 0 and a standard deviation other than 1. That's why it's a non-standard normal distribution. We can convert that to a standardized score, a z-score, that is normally distributed with a mean of 0 and a standard deviation of 1. Now remember, z-score tells us how many standard deviations away from the mean we are. This is your z-score formula that relates your score away from the mean divided by the standard deviation. That's how we find the z-score. So check it out. This woman, let's suppose we have a woman whose height is 68 inches, so a little bit more than 1 standard deviation above the mean. To find her z-score, take that height minus the mean of all the heights divided by the standard deviation. The difference here, the deviation, is 3 inches. Now we're going to divide that by 2.5 inches because every 2.5 inches is 1 standard deviation. So by dividing that out, we get 1.2. Sure enough, a z-score tells us how many standard deviations above the mean she is. Her height is 3 over 2.5. It's 1.2 standard deviations above the mean. To get to 67.5, that's a z-score of 1. This person's at 1.2. Okay, now what we can do, I have a confession. This table that we had down here, it's not really a table for Zippo thermometers. Those aren't what the z-scores were. This is a table for actual z-scores. If you find your z-score, which is your location on the x-axis, this table will find the area under the curve below that z-score, meaning it will tell you what proportion of the entire population is less than that many standard deviations from the mean. So we have a woman whose height is 1.2 standard deviations above the mean, so we go right here and it's 0.8849. So what that tells us is the probability of randomly selecting a woman whose height is less than 68 inches is 0.8849. About 88.5% of all women have heights that are below that height right there of 68 inches. Now we can answer this statement then. We could say then a woman who is 60 inches tall is in approximately the 88th or 89th percentile. So we'll play it safe. We got to make sure we can, it would be the 88th percentile that she's in. Her height exceeds a little bit more than 88% of all the heights in that normal distribution. Now let's shift gears. Let's say we have a distribution of men's heights normally distributed with a mean of 70 inches and also a standard deviation of 2.5 inches. Let's find the percentile of a man who's 6 feet tall. In other words, what percent of all men's heights are below that height of exactly 6 feet tall? Well, we do it in similar fashion. We could draw a distribution of men's heights where the mean is 70 inches, and we're interested in finding the percentile, the percent of the proportion of the whole population that is less than a height of 72. We need that z-score. We need to know how many standard deviations above the mean that 72 is. Well, that's what we use the z-score formula for. 72 minus 70 divided by the standard deviation. Notice this person is less than one entire standard deviation above the mean, so that's why the z-score comes out to be less than 1. We now go to the table to find the percentile. What percent of all z-scores would be less than 0.8? In other words, what percentage of all heights would be less than 0.8 standard deviations above the mean? Again, we go back to the z-table, which is from AP Stats Monkey website, and you have this when you take the AP exam, and we look at 0.8 and we have 0.7881. That means 0.7881 in the entire population is below 0.8 standard deviations above the mean in any normal distribution. So this is 0.7881. So that means 78.8% of all males' heights are below this height of 72 inches. So that percentage. Let's round that to about 79%. Now we could say, who's taller relative to his or her normal population? Is it the woman who's 5'8" or the man who's 6 feet tall? Well, remember, the female, her z-score was 1.2. She's 1.2 standard deviations above the mean. The male's height was only 0.8 standard deviations above the mean. So, let me go back, so sorry. That meant that this person, remember the woman was in the 88th percentile. She had about 88% below her as far as heights go. The man was in about the 79th percentile. So that settles it. She has a more extreme height. She's in a higher percentile. Her height exceeds a greater percentage of women. So the higher the z-score, the higher the percentile. Also, the more extreme the z-score, the more extreme the score is, or the height is, or the time, or whatever. So let's look at this. Two people are arguing over which one did better relative to the race that they ran. Let's suppose we have an individual running in a 200-meter dash. The shape of this distribution of times is normal, and the center is this, and the spread is this. Now, if it's normal, remember, center is mean, and standard deviation is the spread. So that's the mean and the standard deviation. This person ran at a time of 20.9 seconds. The mile race was normal with this mean and this standard deviation, and the person arguing had that time right there. So who did better relative to their distribution? Well, whoever's in the whoever's score is more extremely low compared to the rest of their racers would be the one whose time was more extreme. So all we have to do to settle the argument is to find z-scores for these two people. Now, you can only use z-scores when the populations are normal. If they're skewed, all bets are off. You can't do z-scores. But so here we go. This person was 1.83 standard deviations to the left of the mean, but it is the miler in this case that's more unusual. They were more than 2 standard deviations below the mean, implying that there's a smaller percent of milers who ran faster than him, compared to the percent of 200-meter dash runners that were below this person. So being more standard deviations away from the mean is more extreme, and that's what a z-score will tell us, a standardized score. Now, find the percentage of milers who ran between 260 and 275 seconds. Step 1. Guys, draw a picture of the normal distribution and label it and shade what you're looking for. Even if you're not visual, this is a good thing to do. So this is step number 1. We can see that the area under the curve, and the area is probability, the area is the proportion of the population that's in that interval of times. That's what we're after. So we say, okay, step 2, convert these times or these scores to standardized scores, to z-scores, which tell us how many standard deviations away from the mean we are. Well, wow, I just wrote this guy down wrong. Let's see that. This should be negative 1.25. So this person's time at 260 was 1.25 standard deviations to the left of the mean. This person's time is a positive z-score. They're 0.625 standard deviations above the mean. So we converted the time to standardized scores, to z-scores. Well, now step 3 is to find the proportions under the curve and calculate appropriately. So we can go find the area that's below negative 1.25, and again we can go to this table down here. And we're going to go to the negative z-scores. These are positive. These would be z-scores that are above the mean. And you can see they trap more than 50% of the area below the curve. We need to go to the table with negative z-scores. So we can go to negative 1.25. And we can find that guy right there, negative 1.25. Boop, we got about 0.1056 of the population below it. Do you see what we did? 1.20 is right here. This takes us to the hundredths place. It's very clever. So if we want to know the area below 1.25, just line up this column right here, the negative 1.2, that row, with this column below 0.05, and where they intersect, 1.056, that's the area below a z-score of negative 1.25. So it's pretty clever. So we take that 0.0156, and I'm going to erase this if it's all the same to you, so you don't get that in the way in this next one. We're going back here then, and we put the 0.1056 right there. That's the total proportion of runners that are down in that part of the graph. Now, what's the total area under the curve here? What's the percentile for 0.6 standard deviations above? It makes sense that the answer would be above 0.734. Again, what you would do would be to go back to this table. Now go to the positive z-scores that are on the right side of the mean, and you look up the 0.625, 0.625. Well, that means we're between 0.62 and 0.63. So we're in between these guys, 0.62 and 0.63. And I just covered that up. We're between about 24 10,000ths and 57 10,000ths. So right in between there is approximately 40 10,000ths. So we're going to estimate that it's about 0.734 that's below this z-score right here. So what do? To find the area in between, take the percent that's below this guy minus the percent that's below this guy, and what's left over is what's in this interval right here. So if you put this back on the graph, we'd be looking at about 0.1056 here, and the difference, the 0.6284 is here, so that altogether when you add these two up, you get that total of 0.7340 altogether below that. So if you draw the picture of the diagram of the distribution and shade what it is you need to find, use the z-scores and find proportions under the curve, and either add the proportions or subtract depending on what your diagram is telling you. So a normal distribution must involve a variable whose distribution is bell-shaped. It's got to be continuous, theoretically infinitely many values of x, and it follows the empirical rule that you're going to find about 68%, 95%, and 99.7% of the distribution within 1 standard deviation, 2 standard deviations, and 3 standard deviations respectively. And then remember, a z-score is called a standardized score because a standard normal distribution is one with a mean of 0 and a standard deviation of 1. And all the means in any distribution are 0 standard deviations away from themselves, so that's how we can convert. We use this formula to do it. That's how we get the standardized score. And remember, you guys, z is the position or location on the x-axis in terms of the number of standard deviations for the mean. It is not the probability or the proportion of the curve. We use the z-score to find where we are. If we're at 1.1 standard deviations above the mean, that's where we are on the x-axis. To find what area it traps, you go to that z-table that we saw before, and that will find the proportion that's to the left of that particular z-score. And then finally, you're allowed to compare percentiles of scores from different normal distributions by comparing standardized scores or z-scores to answer the question, which score is more unusual or extreme relative to their particular distribution. I think that's it. There we go. Introduction to normal distributions.